It just did, I think.
Okay, good. So, Alan, I'm just going to read off what Miss Colwell has, and you just tell me yes or no.
That's going down or
starting at
we're going to start.
56.8.
Okay, the problem is that we have them in slightly.
Oh no.
512. Okay, it's good. Start with the blue. So you start with the blue words.
Okay,
I mean the blue numbers.
So, top is 56.8.
Good.
Bottom is 23.7.
No, go down a column.
Ah.
Go down a column.
Okay, 56.8,
Okay.
41.3,
Okay.
43.5,
Good.
48,
Okay.
55.4,
Okay.
45.1.
Good. First
And
column
then-
is good. Second column.
Bottom is 23.7,
Okay.
24.8, 24.5, 24.2, 23.8, 24.4.
Good.
Resonance
Okay.
cavity, we don't have
He
that.
didn't do that. He just did the forks.
Okay.
And I did the programming. So
Force
256.
is 256, 512, 440, 349.2.
Good.
349?
Yes.
339.
We can look at it, it's right here.
Yeah, see if it's 349 or 339.
Yeah, it's 349.
349.
Yeah.
Okay.
So 349.2, 261.6,
Uh-huh.
and 392.
Good. Okay, now, notice, if Sarah will make sure I'm saying this right. 256 and 512 are an octave apart, yes? So their wavelength should be exactly half. Do you notice how close we are?
256 and 5. Oh!
So if you double this number,
No, you would get
0.66,
exactly
you
512.
get 132.
I like that.
Woohoo! We did that right! Yes! Yes, yes, yes. All right. So now, what did I do? What did I do in programming? I subtracted these two numbers.
Yes.
That gave me the resonance cavity.
And to get lambda, what did
And I
you do?
did what? Divided by 100 and multiplied by 4.
Oh my god, I'm sorry.
Yes.
4.
Right. Okay, so now we're going to graph these two, and you're going to see why it doesn't work. And then you're going to tell me what you have to do to change it.
Oh, I'm not hitting it with the metal.
All right, so this is wavelength versus frequency.
If it's into,
And
these
this
two will like drone and
is
make like a weird noise.
frequency, hertz, and this is
Okay.
wavelength.
Almost. It almost is.
What about these two?
Yeah, everything will probably drone, but you can hear it better with the fifth.
Okay, I'd like you to tell me what the shape of that graph is.
That graph is that logarithmic? I don't remember.
No, it's not logarithmic.
Sorry, it's a parabola.
It's inversely proportional.
Oh,
It's a hyperbola.
not a parabola.
Okay. A parabola to the parabolas you'll always get in physics are symmetric. My body's the y-axis, so they're symmetric to the y-axis.
Okay.
If you have a square root graph, that is, your formula has a square root in it, that looks like a parabola to the x-axis. You with me?
Yes.
Okay, then the other technique that tends to happen a lot is that they're inversely proportional. That is, when one gets bigger, the other gets smaller. Does it make sense that they should be inversely proportional?
The longer the wavelength,
The shorter the frequency? Okay?
No, wait, really?
Yeah,
Yes, the lower the frequency. We used to say
Oh.
if it was longer than
Yeah,
it's
lower frequency makes more
Now,
sense.
what
than
happens when
saying-
I multiply, because we gotta talk this through here. What happens when I multiply frequency times wavelength?
You get the velocity.
I get the velocity. Okay, so if I came over here and I multiplied frequency times wavelength, this is another way to know it's hyperbolic.
So, but you're saying that graph is incorrect?
No, I'm saying,
Oh, I thought you said that at the beginning.
I'm saying that we can't use this graph to get the answer, but I'm going to try to make sure you understand why. Okay.
Sorry.
I know, it's just compulsive, isn't it?
Look at that node. And anti-node.
See how smart she's gotten?
Wasn't like this at the beginning of the year.
Look at that standing wave. All right, now, if you notice, okay, now you're going to quit paying attention
Sorry.
to nodes and antinodes. All right? Okay, this is hyperbolic. One way to know if a graph is inversely proportional is, all right, that the product of their xy coordinates are constant. I'll say it again.
Okay.
You can know that a graph is hyperbolic if the product of their coordinates of the points come up to a common value. So if I multiply frequency times wavelength 338, 337, roughly 338, 335, 332, 331, 224. So this one's a little off, okay? Now, if it is close to being constant, then that means that you have an inverse relation. When one gets bigger, the other one gets smaller, all right? Which is what we already know. Now, if we fit a graph to that inverse proportion, it would be a power inverse -1. Yes, okay, so it's a power. Okay, so now what does x to the -1 mean?
Inverse.
It means 1 over x, right?
Yes.
So this number, 332.55, is on average, according to Excel fitting it to a hyperbola, to being y equals 1 over x, right? 0.9968. So that's a pretty nice arrangement. It's a hyperbola. So if they ask you to graph this and this, and you have no choice, you're going to get a hyperbola, okay? And we know that if we multiply frequency times wavelength, we should get a constant wave speed, which isn't too bad for trying to measure through water and hold up little PVC pipes, all right? But what we want is a straight line, yes?
Yes. We always want.
So, we always want a straight line. So if what we have is the readings of wavelength and frequency, how can the slope, what should we graph so that the slope is wave speed?
Okay. We want slope to be wave speed. Wave speed is equal to what?
Frequency times wavelength.
Wavelength. Well,
And we have data on F and we have data on Y. Lambda.
but we need it to be something over something.
So we want lambda equals, right? Because lambda is our y-axis, because it's our dependent variable, because it was your resonance cavity, yes? So lambda equals,
Oh, frequency times 1 over wave speed.
close.
Oh,
Isn't it like that?
wave speed times 1 over frequency.
Yes?
But that's going to be the slope.
So this is the y. So lambda equals VW times 1 over F.
Gosh, darn it, Sam.
Yes? So I want lambda to be y, and I want 1 over F to be x.
Okay.
Then this is my slope. Yes, no?
Yes.
Okay, this is critical, that you be able to change things, all right? So that means that I'm going to add a column called 1 over F. And I think I'm going to do it down here. So I'm going to say 1 divided by
I like that.
frequency, because that's my x-axis.
Yes.
And then lambda is my y-axis. So this would be, okay, what's 1 over hertz?
1 over hertz is, period.
Good, 1 over hertz is 1 over seconds. Yes,
So
because a hertz is per second.
Mm-hmm.
So that means that we'd be measuring it in seconds. Okay? So 1 over frequency is in seconds. Lambda's in meters, right? Okay. So equals, and I'm going to come up here and find my frequency, 1 divided by frequency. And copy that down.
Wow.
Alright, I don't care about this one. Okay, lambda I'm just gonna keep, right? So I'm gonna come up here for lambda and just keep it, and then copy it down. Then we're going to graph these two. Agreed?
Yes.
And if life is right, what should we have?
A straight line.
A straight line. Alright,
Ooh,
Yes.
so now, we want it to be a line,
Linear.
and that's our equation.
That's
Alright.
nice.
So then this is going to be, what is its title? It's always y versus x. So wavelength,
So wavelength versus 1 over frequency, so seconds.
which is versus period, right?
Yeah.
So, and actually, what I should have done up here, no, that was correct, all right. And then over here, my y-axis is wavelength.
Oh, so wavelength is also just equal to wave speed times period. Okay.
All right. See, we're learning things.
Yes, things.
Okay, so this would be the period in seconds. And then the other axis would be, the y-axis would be wavelength, yes? So wavelength in meters. All right, so now, make these sort of the same size. All right, so 0.9968 was the hyperbola, 0.9969 was the line. So for all intents and purposes, we're, got a little bit better, all right? The y-intercept is not 0. So what do you think would cause a non-zero y-intercept in our experiment? Remember, y is wavelength, so why would we have had a slight difference
If we did.
in the wavelength?
So the y-intercept is a positive or a negative?
It is a negative, but it doesn't
Does that
matter, it's
matter?
just very close to 0. But why isn't it 0? What did we do to not make it 0?
We held
We
the
did.
tuning stick, we held the tuning stick above,
Okay, so
like
that
out of
means,
the cavity.
so that means that we might have been at different distances
Like-
above the cavity.
Had we held
to make
it, like-
resonate.
At this, inside, like if the cavity were big enough and we held it inside the cavity, like
No,
right
because
here,
which
we
way
could-
is the
Oh,
vibration?
it's gotta be this way,
It's gotta
sorry.
be that way.
But if it was at the same distance every time,
Right, or above it, okay? So that's the big error.
okay,
The
so.
big error is that, in reality, that tuning fork should be right smack there.
But it can't
But if you
be.
put it there, then you
It's gonna
stop the
stop,
tuning
right?
fork, all
Yeah.
right, and it won't vibrate. So then, I love you, sweetheart, but you're forgiven because you had that fancy
Oh.
program, all right? So, and also, there's a problem reading the water, right? Because
Yeah,
you're
reading the
reading,
water was a little difficult.
yeah,
I
because
could've
you're
done,
reading through the water, through the plastic, and all that kind of mess, all right? So, those are your two sources of error. But I believe that the reading through the water is hard, but where the tuning fork was held above the end of the tube is the biggie,
Ooh,
okay?
We got 20 minutes left.
Okay, so now I'm gonna print for you, all right?
Thank you.
May I go use the restroom?
Yes, you may.
Okay, let's write this lab. Also,
Alright.
oh, are we good to go on these guys?
I
Hi.
don't know if they, okay, just a minute, let me think this through. Turn them off for the minute. And
Okay.
let me figure out what I wanna do.